Okay, so in this part of the lecture, we're going to look at solving matrix equations. So just to remind you, in a previous lecture, we saw how to rewrite a system of linear equations, for example, this one over here, as a matrix equation. So we had our matrix, which represented the coefficients of each of the linear equations. We had a vector, which is our variables, and over here we had our vector, which represents the constants, which in this case are all 0 on the other side of the equals. So now what we need to do is, if we're given a matrix equation, how do we solve it? So it turns out to be helpful to just remind ourselves about how we solve simple scalar equations for example, things like 2x is equal to 3. Now you might think that if you're solving 2x is equal to 3, then what you do is you just divide both sides by 2. But that's not actually what you're doing. That is a quick shortcut, but when you were first taught how to do this, what you were told was you need to multiply the left-hand side by whatever is going to give you 1 when it multiplies by 2. So you need to multiply this by the inverse, or the reciprocal of 2. So what you actually do when you're solving an equation like this is you times both sides by a half. And then on your left-hand side, you get a half times 2, which is just 1, so that gives you 1x. And on the right-hand side, you get a half times 3, which is 3 divided by 2, which is why one always thinks of it as just dividing through by 2. So you end up with 3 over 2, and obviously our 1 doesn't count, so here we know we've got our x is equal to 3 over 2. So there are two things that are really going on here. The first is that you need to have some idea of what the inverse of 2 is, which is easy to do. When we're dealing with scalars, we have that a half is the inverse of 2, by which I mean the multiplicative inverse. What do I mean by multiplicative inverse? I mean it's the thing that you times 2 by so that you get the multiplicative identity, which is 1. So you have the situation that half times 2 is equal to 1. So you need to know what the multiplicative inverse of something is in order to do this whole solving thing. The other thing you need to know is what the multiplicative identity is. So you need to know that there's this special number 1, which is going to give you this situation over here. So that probably sounds very complicated, and you do this sort of thing in your head without even thinking about it, but it's useful because now we're going to apply the same reasoning to solving matrix equations. Okay, so what do we need to do? Suppose we've got a matrix equation of the form A, which is some matrix, times x, which is a vector, and that's the thing we're trying to solve for. We're trying to solve for that x vector is equal to some vector of constants. Well, what we need to do is we need to find some matrix a to the minus 1, which I'm thinking of here. So I'm not thinking of this as 1 over a. I'm thinking of this as the inverse of a. Again, the multiplicative inverse of A. So I want to find this magic matrix A inverse, so that when I take A inverse times A, what I really just get is some kind of matrix 1. But because I'm going to multiply on both sides, I'm going to have my A inverse times A on the left is equal to, and then I've got this A inverse because I've multiplied on both sides by the inverse. And then hopefully we need this thing to be equal to some kind of 1. And I'm going to put a little arrow over it because obviously it's going to be a matrix, not a scalar. So we want to end up with something that looks like this. And then we can just do this multiplication here with our matrix multiplication. And we end up with the vector that we're looking for is equal to inverse of A times B. So that's the plan, and it follows the logic of doing ordinary scalar solving for equations. So the two things that we need to figure out is, can we find an inverse for our matrix, and can we find some matrix that behaves like the multiplicative inverse, the multiplicative identity in Scalar? Well, luckily we can do both of these. Now we're only going to look at solving matrix equations which have square matrices, because square matrices are the only things you can really find inverses for. If you think about that, you'll figure out why I'm saying that. So what is the identity matrix? Well, we already sort of saw it a little bit. It's a square matrix with ones on the main diagonal. So the main diagonal is the longest diagonal, and everywhere else is zeros. And the thing to notice about the identity matrix of whatever size is that if you take your identity matrix times any other matrix other than all zeros, you will always, ignore what I just said, you could take any other matrix, you will get that matrix back. So if I do the matrix multiplication here, I've got a 1 times A plus a 0 times C, so that's an A, 1 times B plus 0 times D, that gives me a B, 0 times A plus 1 times C gives me a C, 0 times B plus 1 times D, voila. So when we're talking about matrices, and we're thinking about a multiplicative identity, this identity matrix of the appropriate size acts like 1 does when we've got scalars. Okay, so we've solved that bit of the problem. Now we need to solve the problem of finding inverses. So we're going to start by looking at the 2 by 2 case, and we're going to solve that reasonably explicitly. And then I'm going to talk through how you would find inverses for 3 by 3s, and that's as far as we're going, because it gets a bit crazy. And mostly nowadays one would just ask a computer to tell you the answer. But we need to have an idea of what's going on here for some of the stuff we need later. Okay, so suppose we have some 2 by 2 matrix, A, which has entries A, B, C, D, and we'd like to find the inverse. What does that mean? Well, it means that we want to find a matrix, in this case, this one here, X, Y, Z, W, which when we multiply A, B, C, D by, gives us the identity matrix. So this is the same as saying if we've got 2x is equal to 1, what we want to do is find this x so that when we multiply 2 by, we get 1, in which case this x is equal to a half. I could have done this the other way around, so I could have put my x, y, z, w on the other side and we'd find the same answer. I'm just choosing it to do it like this because we just tend to usually put the thing that we're solving on the right-hand side of the multiplication, but you could work this either way. So although you might not realize it, we're looking at a system of linear equations. Let's just write them out. So if I look at the matrix multiplication of my 2 by 2 times my 2 by 2, I'm going to end up with, I've got A times X plus B times Z. So that's AX plus BZ, and that has to be equal to 1. I've got AY times BW, plus BW, and that has to be equal to 0. I've got CX times DZ, plus DZ, sorry, and that has to be equal to 0. And then finally I've got CY plus DW, and that has to be equal to 1. And if you felt particularly like torturing yourself, you could go ahead and solve this using Gauss reduction. So we'd put together, so notice you've got 4 variables, so this is a 4 by 4 augmented matrix that's going to rock up here. We'd have A, 0, 0, B, we've got a 1 here, we've got a 0, A, B, 0, and a 0. Now I've got a C, 0, 0, D, and a 0 there, and a 0, C, D, 1, and a 1 there. So yeah, as I say, if it floats your boat, feel free to do this Gauss reduction, but I would never ask you to do this because 4 by 4 is just too much. But if you do it, The important thing, and this you do have to just know, is your solution will look like this. You will have that x is equal to d over AD minus BC, y is equal to minus b over AD minus BC, z is equal to minus c over AD minus BC, and w is equal to a over AD minus BC. Okay, bear with me. What does this tell us? This tells us that if you have any old 2 by 2 matrix with those elements, then you can find an inverse most of the time. And that inverse will look like this thing over here. So we've got this scalar thing over here, which is 1 over AD minus BC, and you just multiply each of the entries in this thing by that. So notice what you've done, so this is kind of how I remember it, is you swap A and D, and you give B and C a minus sign, but you don't swap them. Okay, so that's how you figure out the entries in that matrix, and then you multiply by this thing over here. Now the important thing to notice about this scalar over here is this term over here, because you will only be able to find an inverse if AD minus BC is not equal to 0, because otherwise you'd have 1 over 0 and you'd be multiplying by something we don't know what that is. So this is a kind of a crucial thing. In scalars, the only number that we have that doesn't have a multiplicative inverse is 0, because we can't do 1 divided by 0. But it turns out that there are plenty of matrices which look absolutely normal, but if you look at their 2 by 2 form and their AD minus BC, that's 0, so they don't have inverses. So scalars, everybody except 0 has an inverse, but matrices, plenty of non-zero matrices don't have inverses. So the first thing you're going to do anytime you think you might need to find an inverse is check, does this bunny actually have an inverse? Okay, so we've looked at the 2 by 2 case. So I do expect that if I hand you a 2 by 2 matrix, you can find its inverse, and you can just go straight ahead and use this form over here. You don't have to do anything complicated, just plug in the numbers. I mean, first check that it has an inverse, obviously. Yeah. The n by n case is quite a lot more complicated, as I said earlier, and you might well just use a computer. But there are going to be some concepts within how one finds it that we will need, and that you might well also need in courses like chemistry, or if you do anything kind of modeling wise in bio. So we're going to talk through it. So our first step, because we've seen that not all matrices have inverses, even if they're square, is to decide if they do. And we'd like to have something a little bit like this AD minus BC, which tells us in the 2 by 2 case whether or not it has an inverse. So we'd like to have some quantity like that that we can just calculate and go, okay, yes, I can find an inverse for this matrix. No, I can't find it. And the quantity that we have is called the determinant. So it's a number that you calculate based on the entries of a matrix. And if the determinant, this number that you've calculated, is non-zero, then you can find an inverse. If it's 0, you can't. So the determinant, there's different notation that gets used. So usually det A, or without parentheses, and sometimes you will see this used, so the little straight lines. That's more used when you're actually writing out a matrix. So for example, if I have a matrix A that we've seen a lot of before, so I've got A is equal to A, B, C, D, I would write it like this. Det A is equal to, and now here I'm using these kind of, they look like absolute value signs around the entries of my matrix, and we've already seen that for 2 by 2 our determinant is AD minus BC. So it's just you multiply along the diagonal AD, and then you subtract from the diagonal going in the other direction. Okay, so that's pretty straightforward, and this you need to know. So what about the 3 by 3 case? So as you go up in dimensions with your square matrices trying to find the determinant is defined kind of recursively. So you unpack your bigger matrix into determinants of smaller matrices. Let's just look at the 3 by 3 case. We won't go further than that, but you can. So if we've got, so here our matrix A is this big thing here, D, E, F, G, H, I, and we want a determinant of that. So again, this is just writing out the thing that we're going to calculate. Now we're going to have 3 terms because it's 3 by 3 in this case. And we're going to have coefficients on each term, A, minus B, and C. And then we're going to find mini determinants to multiply by. Where do those mini determinants come from? Well, the idea is to imagine that, for example, when you're looking at the A term, you ignore everything in the first row and the first column. So the column that A belongs to and the row that B belongs to, and you take the determinant of what's left. Okay? Now if you're going to work out the B value, now you ignore everything in the same row as B and also the same column as B. So what you've got left is DG and FI. So that's that bit there. And finally, if you're working out the C term, you ignore everything in the same row and the same column as C, and what's left is DEGH. So it looks a bit messy, but it's entirely doable, and also you'd mostly use a computer. But just to give us a little bit of practice, let's find the determinant of this matrix over here. So our determinant of A is going to be, all right, so the first thing is we look at our A, which is in this case minus 3, and we want to times it by the determinant of, so I'm just going to put lines here to say I'm ignoring the first row and column, and we want the determinant of 0, minus 2, minus 4, 1. And now we're going to say, now the important thing to remember here is this minus sign. So now we've got minus B, so that's going to be minus 2 times, and now we ignore everything in this first row, second column. So we've got the determinant of minus 1, minus 2, 3, 1. And then finally, we want to have plus 5. And we ignore everything in that column, that row. So that gives us the determinant of 1, 0, 3, minus 4. Okay, so it's a bit tedious, but let's keep going. All right, so here I've got my minus 3 times, now the determinant of a 2 by 2 is just 0 times 1 minus 2 times minus 4, so that's minus 8, I think. Let's just check. Yep. Now I've got minus 2 times minus 1 minus 2, so that's minus 1 plus 6, so that's 5. And now we've got plus 5, and I've got a 4 minus 0, which is just 4. And if you plug all that together, you get minus 6. So, as I say, usually you would use a computer, but working through this once is, a growing experience. Going to make your brain stronger. And now we can tell that this matrix A does have an inverse. So yay. Now we could go ahead and find the inverse. Okay, so part of why we need the determinant is not only to tell if the matrix has an inverse, but it's integral in computing the inverse. So if you remember when we did our 2 by 2 case, the determinant we really had, so if we have our 2 by 2, which is, well, let's not call it A, let's call it B is equal to A, B, C, D, if you look at the formula that we have that the inverse of B is equal to 1 over the determinant of B times dA minus BC. So we actually use the determinant in the calculation for the inverse, not just for telling us that we could find the inverse. So how does this apply to n by n matrices? Well, we have the same factor coming up in our inverse, 1 over the determinant that we had in our 2 by 2 case, so that's nice. But in place of this kind of swapped version of our original matrix, in the n by n case, we calculate a new matrix called the adjoint. And it's calculated from the entries of A. Now we're only going to look at calculating the adjoint for 3 by 3 case. If you go further, then you will have kind of seen sort of how it works, and you can figure it out for the bigger cases. Okay, so just take a breath when you look at this. It's not as bad as it looks. So the first thing that we do is we compute what's called the cofactor matrix. And there's more determinants here. Sorry about that. But it uses the same ideas that we used in computing the determinant. So let's have a look. So I'm going to have my matrix here is A, and here I've used slightly different notation. So my matrix A is A11, A12, A23. No, it's not. A13, A23, what am I talking about here? A21, A22, A23, A31, A32, A33. Okay, so that's what our matrix A looks like. And what we want to do is use it to compute this cofactor matrix. Now notice what's happening in our cofactor matrix. Each of our elements, our entries in the cofactor matrix, is a 2 by 2 determinant. So where are the entries of that 2 by 2 coming from? Well, if you have a look here, so this is really the C11 entry. And what did we do? Well, we looked at our A matrix and we said, okay, let's ignore everything in the 1, 1 column and row and take the determinant of what's left. And then we did the same thing. So if you have a look over here, this is the C12. So this says, look at your original matrix, ignore everything that is in the first row and the second column, and take the determinant of everything that's left. So it's using the same trick that we did for the determinants. It's just there's a bit more because now there's 9 entries instead of only the 3 that we used for the determinant. But it's exactly the same idea. One of the key things to note is that there is a sign thing happening here. So our top row goes plus, minus, plus. The next row down goes minus, plus, minus. We get plus, minus, plus. And we need to remember those factors. Okay. Let's do one example. I'm going to just finish up how we find the inverse from this, and then we'll do the example. Okay, so once you've found the cofactor matrix, that's not quite the adjoint. The adjoint is the transpose of that, which means you swap the rows and columns. So we'll see what that looks like as we do this example. So here's a summary of everything. Mostly useful, I guess, if you are working from your notes during a test or exam. Okay, so let's calculate the inverse of the following matrix. Okay, so we know that our inverse is going to be 1 over the determinant of A times the adjoint of A. Now, if you go back in the notes, you'll find that we've actually already found the determinant, so yay. So now we need to find the adjoint. And to find the adjoint, we first need to find the cofactor matrix. So our cofactor matrix, C, is going to be, and I'm going to copy from notes here because otherwise bad things will happen. All right, so I want to think about my C11 entry. So the first thing that I do is I say, okay, I'm going to ignore everything in the 1, 1, the first row, first column. So ignore everything here. And I'm going to take the determinant of 0, minus 2, minus 4, 1. Then I'm going to find my C1, 2. So ignore everything in the first row, second column. So first row, second column gets ignored. So I find the determinant of minus 1, minus 2, 3, 1. And I keep going. So now I'm going to find the determinant of minus 1, 0, 3, minus 4. And now moving on to the second row, so now I'm going to ignore those entries, and I'm going to find the determinant of 2, minus 5, minus 4, 1. And you can see how this is going. I'm just going to copy down the rest. So I've got minus 3, minus 5, 3, 1, minus 3, 2, 3, minus 4, 2, minus 5, 0, minus 2, minus 3, minus 5, minus 1, minus 2, and minus 3, 2, minus 1, 0. And it is really tempting at this point to heave a sigh of relief and say, okay, well, at least I've written this thing down, but don't forget the signs. So this is really important. This is going to be plus, minus, plus, minus, plus, minus, plus, minus, plus. Phew. Okay. Let's add another page here. This is one thing when you're working with matrices, you do use up a lot of paper. So if you work this out, which I will leave you to do in your copious free time, you will find that your cofactor matrix ends up looking like minus 8, minus 5, 4, minus 18, 12, minus 6, minus 4, minus 1, 2. And so now we need to find the adjoint, which is the transpose of C, which says every row becomes a column and vice versa. So what does this look like? We take our first row and that becomes our first column. So that's minus 8, minus 5, 4. Now we take our second row and it becomes our second column, minus 18, 12, minus 6. And finally, our last column is minus 4, minus 1, 2. Hooray! So, putting this all together, what we have is that our inverse for our matrix is 1 over our determinant, and we found the determinant was minus 6. So we've got 1 over minus 6, minus 8, minus 18, minus 4, minus 5, 12, minus 1, 4, minus 6, 2. Hooray! We have found the inverse of a 3 by 3 matrix. So what I would like you to do for a little bit of homework is to actually multiply out. So show that if you do the multiplication this way, you get the identity, and if you do the multiplication the other way, you also get the identity. So this is just going to give you some matrix multiplication practice. Okay. So, well, in the next little bit, we're going to point out why it's useful to have the inverse of a matrix, because you might be thinking, but I know how to solve linear equations, I can just use substitution. But the trick comes in when you have a situation where you might have the same looking equations on the left, but you're solving for different values on the right. And we'll see shortly that it's super useful to actually just have the inverse, because then it makes you don't have to repeat calculations, you just have the thing that you want. But maybe take a little break now, make sure that you're comfortable with everything up to now, and when you're ready, come back and we'll finish off the last little bit. So let's have a look at solving these systems of equations. Now we can write these out as matrix equations. So we would write out this first one as minus 3, 2, minus 5, minus 1, 0, minus 2, and you'll notice you should be getting kind of familiar with these entries by now. And I can just straight copy this. And now I'm looking at this. Now notice that all our hard work means that we have actually found the inverse for this particular matrix. That's what we've been working on all along over here. We just found the inverse here. So let's just grab that here. And the power of having found this inverse is that it makes life super simple when we're solving. So let me just put our inverse over here. Is if we look at this equation over here, we can dive straight in and solve it, because what we do is we're going to multiply on the left by our inverse. So remember that our A is this thing over here. So if we take our A inverse times our A times our XYZ, then we've got to also have our A inverse times our 3, 4, what was this? 3, 4, 3. But we know that this is the identity matrix, so this is going to end up giving us that XYZ is just equal to our A inverse times 3, 4, 3. So obviously remember we did a fair amount of work to work out that inverse, so it's not like we're just doing this super quickly, but now we can just do this multiplication, and if you do that you'll find that XYZ is equal to -6, -5, 1. And a valid thing to say at this point was, well, it would probably have been quicker to just Gauss reduce the original system of equations. But notice that now we can dive straight in and solve this equation, which has the different right-hand side, immediately by simply multiplying the right-hand side by the A inverse. So to solve this equation, we solve that XYZ is equal to our A inverse times our new right-hand side, which is 3 minus 1, 3. So if you have right-hand sides that are changing, so you might be wanting to do the same calculations, but for a bunch of different right-hand sides, having the inverse is super quick, because now we just do this multiplication, and you'll find that XYZ is equal to 954. And you can imagine probably you're breaking even if you've got two calculations to do, but by the time you've got 3 or 4, and you're just reusing your inverse a bunch of times, it's a lot quicker than redoing the Gauss reduction every time you want to find the solution for a new right-hand side. So that's one of the key reasons for finding inverses. Obviously, in the real world, computers find the inverses for you, but understanding what is going on, that you're using the determinant, that not all matrices have inverses, is pretty important. So just to finish up a little bit, why did I put you through all this? Because you're probably feeling like this was cruel and unusual, this determinants and cofactors and all this stuff. Well, the reason I did it is because if you go on in chemistry or some branches of biology, you will encounter these concepts again, and they will be used, but they'll be in quite a complicated situation. You won't just be looking at the concepts, you'll need to be familiar with them so that you can apply them. So I spoke to a bunch of the lecturers in MSP, and they were like, please cover this material so that students have at least seen it. You might need to revise it, you might need to look at these notes, but hopefully you'll have enough of a grounding that you won't just feel completely at sea. So I know it's been a bit tough, but I hope that it works in the long run. Okay, so just taking out from this lecture what you need to know. You need to know how to find the inverses of 2x2 matrices for sure, using the formula. You don't have to do the whole solving systems of equations, just use the formula. And you need to know 3x3, because I want you to understand about finding the determinant and then how you use the determinant, and then the ideas of the determinant to calculate. This is just to give you practice and kind of cement the ideas that we've done in this course for future work. And then finally, probably the most important thing, I mean, the whole point of this lecture is you need to know how you use the inverse to solve matrix equations of this form. All right, so we've done quite a lot. Please take time to consolidate it, do some examples, and remember, just like if you want to get strong, you have to go to the gym and you have to kind of push yourself. If you want to get good at maths, you do have to push yourself sometimes. So that's been one of those lectures. All right, see you next week. Bye.